In this video, we are going to author a simple Blender native model. We can observe some anomalies because the exported FBX model does not align with the convention expected by the default creation parameters. To address this, we follow a two-stage workflow. Some mesh editing in Blender and some editing on the asset tool. We begin by loading the model into Blender. As a best practice, we may want to create a backup copy of the model before making any modifications. Next, we clean up the hierarchy by removing nodes that are intended only for rendering in Blender. The key principle to keep in mind is that any hierarchy modification should result in a scene graph that remains an embedded subgraph of the original hierarchy. In practice, this means that we can add or remove nodes, but we should not alter the parent-child relationship of existing nodes. For this particular model, we remove all camera nodes and the background reflection objects. We then select the chassis and using Blender's mesh editing tools, we separate the left and right rear view mirror submeshes and we make them children's node of the chassis mesh. For this model, the chassis geometry is simple enough that it can be accurately approximated using a single convex hull collision shape. In some cases, however, the geometry may be too concave and must instead be represented by a multiple convex collision shapes. We will cover that process in the next video. Next, we add the appropriate naming flags to each component as we did in the previous video. Once the hierarchy is prepared, we export the model as an FBX file and import it into the asset tool. The first issue we notice is that the FBX exporter does not generate proper lumber materials. We correct the material at this stage. While this step is not required for the simulation itself, it improves the visual appearance of the model within the asset tool rendering system. We then inspect the imported model and verify that all collision shapes have been generated correctly. We observe that the chassis collision shape is correct, but the tire collision shapes are not. To fix this, we apply a pivot rotation to each tire so that their local axes match the convention expected by the physics engine. Specifically, the x-axis should be perpendicular to the tire plane and the up-axis should be aligned with the chassis up-axis. We do the same to the 3 remaining tires. When a pivot rotation is applied, the tool automatically adjusts the transformation of the immediate children to preserve the original orientation. This includes center of mass, local mesh geometries, joint offsets, inertial matrix, collision offset, and so on. Therefore, we reset the orientation offset of the collision shape and we recreate them. We again repeat the same process for the remaining 3 tires. After completing this adjustment, we are now ready to configure the drive train, define the map distribution, set up helper nodes, add custom property nodes wherever the application-specific animation or simulation parameters are required. For a detailed explanation of this example, please refer to part 1 of this tutorial series. The entire authoring process does not need to be completed in a single session. You can iterate between authoring and testing by saving the model, running it in the application, and making incremental improvement with each pass. Once the model configuration is complete, we test it in the application. Although this model represents the iconic Ferrari Testarossa, its simulation behavior will not yet resemble that of a real motor vehicle. At this stage, the tire and the engine are simulated using simplified linear rigid body models. To achieve more realistic vehicle dynamics, we need to introduce non-linear tire models that replace the standard Coulomb friction model. We will explore more these techniques in future videos. For now, this vehicle behaves more like a robot with rigid plastic tire than fully realistic automobile. In the next video, we will demonstrate how to create and author concave shapes. Until then, thanks for watching.